Hello, my name is Ligia Bernardet, and I am the Deputy Division Chief for the Earth Prediction Advancement Division. I'm going to talk to you about various ways in which GSL engages with the community to improve Earth system prediction and ensure impactful outcomes from its work. My talk will cover our engagements with the Earth Prediction Innovation Center, or EPIC, the Developmental Testbed Center, DTC, the Hazardous Weather, Hydrometeorology, and Aviation Testbeds, the Joint Center for Satellite Data Simulation, the UFS Community Governance, and Social Science. At the end, Dave Turner will discuss GSL's role in leading collaborative programs. Starting with EPIC. EPIC's mission is to be a catalyst for community-based research and model development using the UFS. Soon, the EPIC contract will be awarded, and work will start to support the UFS infrastructure and cloud and accelerate the R2O process to the National Weather Service. At GSL, our plan is to support the onboarding and transition of the EPIC contractor as a new UFS community member that's responsible for supporting open community model development, ensuring cloud-ready code, and providing access to data and tools. As a member of the community and leader in short-range weather, physics, and atmospheric composition research and development, GSL will continue to contribute scientific and evidence-based model improvements to the community. We are committed to being a prominent contributor to the UFS as a way to easily work between the research and operation communities to accelerate transition of innovative science. Finally, we will gradually transition aspects of the UFS community support effort from DTC to EPIC, which leads us to our next topic, the Developmental Testbed Center. The DTC's mission is to connect the research and operational communities working on NWP to expedite the rate of transfer of innovations to operations. The DTC is jointly sponsored by NOAA, the Air Force, NSF, and NCAR, and has staff at GSL and at NCAR. The DTC has three main work areas, which are strongly interrelated. It provides community support to a number of NOAA operational modeling systems and components with the goal of making those accessible to a broader community of users and developers. It supports various aspects of the UFS, such as the short-range weather application, which is the limited area configuration, the global medium-range weather application, aspects of the hurricane application, the CCPP, and MET+. Regarding CCPP and MET+, DTC is responsible not only for the support, but also for the development. It also supports legacy modeling systems that will be phased out as NOAA completes the transition to the UFS, such as HWRF and GSI. This O2R activity makes it possible to harvest innovations from the general community, which we can then assess through our testing and evaluation activities. Finally, the DTC promotes community interactions by organizing workshops, hosting a visitor program, and issuing a quarterly newsletter. This work addresses one of the comments from the last GSL review as it puts in place a strategy to leverage the community to improve NWP. Here's an example of how the DTC works with the academic community, the private sector, and the Weather Service to support the transition of research to operations and vice versa to help improve models. DTC visitors from UCLA diagnosed problems with the HWRF radiation, namely clouds were too transparent to radiation. DTC tested a replacement scheme, but it degraded the forecasts. But after DTC included a partial cloud in the scheme, the model improved, and both innovations were transitioned to operations in 2015. Then DTC had new visitors from the private company AER, who worked on the updated model and improved the cloud overlap method. DTC tested that, and it was transitioned to operations in 2018. The visitors returned to DTC for additional work, which again resulted in a transition to the 2020 HWRF. The DTC also collaborates with other testbeds, such as the Hazardous Weather Testbed, who evaluated datasets produced in their spring experiment to help inform future ensemble design. The 2016 evaluation compared multi versus single physics ensembles and showed that, in spite of its theoretical superiority at that time, the single physics ensemble performance lagged behind its multi-physics counterpart. This result informed the need for future development in stochastic processes for single physics ensembles, as previously discussed by Joe Olson. The 2018 datasets were used to compare UFS and WRF-based ensembles and showed that the UFS performance was comparable or better than the WRF ensemble, forming a foundation for the development of the UFS-based RRFS, which is planned for operational implementation in a couple of years. Finally, here's a highlight of the UFS medium-range weather and short-range weather application releases we issued in 2020 and 2021. The DTC worked closely with a multi-institutional team from the Weather Service, NCAR, and NOAA laboratories and had the roles of co-leading the release, developing the workflow for the short-range weather app, creating test cases, making the code available on a variety of platforms, including Mac laptops, developing documentation, and providing user support. GSL also collaborates with other NOAA testbeds. We participate in the yearly spring experiment organized by the Hazardous Weather Testbed and the Flash Flood and Intense Rainfall experiment organized by the Hydrometeorology Testbed. We supply real-time research forecasts containing GSL's latest scientific and technical innovations and attend the experiments to evaluate all experimental guidance. This figure, created during the 2020 HWT experiment, shows a comparison between FE3-based forecasts of composite reflectivity and observations. GSL submitted 4 forecasts from 4 configurations, using different options in horizontal diffusivity and initial conditions. As expected, forecasts using the HURR initial conditions shown on the bottom row agree better with observations than forecasts initialized from the GFS on the top row. The figure on the right, created during the 2020 HMT experiment, shows QPF produced by the GSL configurations on the bottom row as compared to observations and a configuration submitted by EMC. GSL also contributes to the Aviation Weather Testbed. In 2020, we contributed the HURRI, and its forecast probabilities were compared against the operational HREF and observations. The experimental HURRI showed better reliability in the 24-hour probabilistic forecast of convective coverage than the operational model, both for sparse, shown at the top, and medium convective coverage at the bottom. Another aspect of our community engagement is with the Joint Center for Satellite Data Simulation. We contribute development to the Joint Effort for Data Simulation Integration, or JEDI, which is an architectural cornerstone of the UFS. We helped create JEDI Unified Forward Operators, or UFOs, with a focus on conventional observations. This table shows the progress, illustrated as green cells, of JEDI's ability to process various types of observations. The bottom plots focus on 2 types of observations: 2-meter temperature and specific humidity from METARs. The scatter plots indicate an excellent match between the forward operators between the emerging JEDI and the GSI, which is encouraging as it will allow the adoption of JEDI in upcoming UFS configurations. You have already heard a lot about the UFS from previous speakers. Here, I would like to highlight our key contributions to defining the direction of the modeling system. We participate in the UFS Steering Committee and we co-lead the SRW-CAM application team and the Physics and System Architecture working groups. Members of our staff also participate in the Atmospheric Composition, Physics, and Verification working groups. GSL also contributes to the governance of the UFS R2O project by coordinating the RRFS activities within the SRW-CAM sub-project. GSL goes beyond simply creating model guidance and uses social science to make its products more usable and impactful. We post-process our ensemble models to create PDFs and other probabilistic products. Forecasters use this information to provide decision support services, and our social science research assures that they understand the products, can communicate their probabilistic nature, and have access to verification information to shape their confidence on the material. We then follow the information as it flows to core partners and make sure they are able to understand and use that information to make decisions with the best outcome for society. GSL was involved in 2 projects over the past few years. Each was led by a social scientist at NCAR to research the information needs of forecasters as well as their DSS partners. The images show forecasts for the onset of snow. The left and center images show the earliest and latest times that snow is expected to start. The right image shows that snow is expected to start at different times depending on the location. GSL has a long tradition of working closely with those forecasters who will use the applications and tools we develop. Here is a final example of interaction with forecasters. In this case, was the hazard services software on ALIPS. We collected feedback through a number of demonstrations, meetings, and tests, and incorporated it onto the development process to achieve a superior product. I presented several aspects of our engagement with the community, and now I'd like to turn it over to Dave Turner, who will talk about GSL's role in leading collaborative programs.
Hello, my name is Dave Turner. We just heard a very nice overview from Lesia about a variety of different collaborative efforts that we have going on within the laboratory. The laboratory is also leading several different collaborative programs, and I'd like to speak to you a little bit about them today. I'm the manager of one of those programs, the Atmospheric Science for Renewable Energy program. The Atmospheric Science for Renewable Energy program was initiated about 10 years ago. It has about a $2.8 million annual budget and includes participants from many of the different laboratories, actually all 4 of the laboratories in Boulder, the Physical Sciences Lab, Global Monitoring Lab, Chemical Sciences Lab, and our lab. I'll speak more about that one in a moment, but we also have a boundary layer program that's much newer, was initiated in 2018. It has a smaller annual budget, but we're working to increase that now, and it includes 3 of the ESRO labs, the Physical Sciences Lab, Global Monitoring Lab, and GSL, as well as the Air Resources Lab and the National Severe Storms Laboratory. The third program I'll speak a little bit about is a fire weather program. That's a new program that's being developed really in the last sort of 8 months. It has potentially a $25 million annual budget. It'll include virtually all of the OAR labs, as well as NOAA Satellite Service, NESDIS, and the National Weather Service. The Renewable Energy Program is motivated by the fact that the U.S. electricity demand continues to increase with time. As we look to the future, that increase does depend on a variety of different assumptions that are made. We could be in a high demand scenario where the increase will be largely linear with time, or in various other scenarios which would have the demand sort of tipping over and leveling out with time. Regardless, there's a strong desire to move toward more renewable energies, renewable energy generation, and integrating this into the electrical grid. It's a priority of the current administration, and it's one way to mitigate climate change. There's a variety of economic benefits that really make this worthwhile for the community. In a general sense, renewable energy is very cost competitive. When we look at the levelized cost of energy, you can see that wind energy and utility scale solar are very affordable and much more affordable than some of the other fossil fuel type generation sources. The challenge is that renewable energy from wind and solar is highly variable. It depends strongly on the weather conditions. To integrate renewable energy into the electrical grid efficiently, you need to have accurate day-ahead forecasts so that the energy providers know how much energy to expect from a renewable resource such as wind. This requires high spatial resolution weather forecasts, especially since many of these wind turbines are in complex terrain and clouds are often very local and very small scale. That makes the HRRR an ideal model for providing these renewable energy forecasts. That was the origin of the Atmospheric Science for Renewable Energy. It was an integrated multi-lab applied research program that's really aiming to improve our downloading solar and our surface to 300-meter wind forecasts. in the 1 to 48 hour forecast horizon of the HRRR, so really for that day ahead forecast. This program has a very strong emphasis on the boundary layer turbulence and subgrid scale clouds. As the HRRR's model primary customers is for the convective community for doing convective forecasts, our constraint is to do no harm. We don't want to impact the quality of a convective weather forecast in our attempts to improve the wind speeds at 100 meters. Fortunately for us, generally improving the boundary layer physics to get better wind forecasts, to get better boundary layer cloud forecasts actually improves our convective weather forecasts. Over the last several years, we have over 35 published papers that have authorships that include people from multiple laboratories, a real success through NOAA. And the nice thing about ASRI is it spans the entire technical readiness range. It helps to propagate things from basic research ideas all the way through to operations, and so really facilitates that research to operations transition that GSL is well known for. The ASRI program has a strong collaboration with the Department of Energy, and in particular, the Energy Efficiency and Renewable Energy Office. In that office is the Wind Energy Technology Office, and they've been a major partner for us for the last decade. WEDO has partially supported these wind energy forecast improvement projects, field campaigns that have a variety of different foci to really improve our ability to simulate and predict hub height level winds. The first WFIP campaign happened in 2011 and 12 and really had a focus on assimilating data in those lowest levels. In 2016 and 17, the second WFIP campaign happened in the Oregon and Washington State area with a focus on complex terrain and improving our representation of winds in that type of situation. WFIP 3, which will happen in 2022 and 23, is going to focus on offshore challenges with wind energy, so in particular off the East Coast. You can see these data sets allow us to use our model testing framework. After we collect a nice comprehensive data set like through the WFIP campaigns, we will often be in a development loop where we'll use single column models to do some initial evaluations of new changes to the physics. If those prove to be successful, then we'll do case studies with the 3D model and evaluate those in the domain of interest where the field campaign happened. Again, if that shows to be promising, then we'll start looking at those same case studies to see, did we have any adverse effects outside the domain, or are all the changes positive? If all of those look good, then we'll start doing some longer term testing with multi-day retrospectives and even multi-month reforecasts. I outlined this model testing framework as a way what we're doing here within ASRI, but this is actually the model testing approach that we use throughout GSL anyway. Continuing with the Department of Energy collaborations, we're working to build a stronger relationship with the EERE's Solar Energy Technology Office, a sister office to the Wind Energy Technology Office. Myself, I've had a long-term relationship with the Office of Science through the Atmospheric System Research Program, and we use heavily the data from the Atmospheric Radiation Measurement Program sites both in north central Oklahoma and its mobile facilities in different locations. And one of the reasons that the WEDO staff in particular likes working with us is that we provide a way to facilitate how DOE-supported research can actually work to improve operations and operational forecasts for the wind energy community. As an example of some of this research, I wanted to highlight two examples. One is on wind ramp forecasts. So a wind ramp is a sudden increase or decrease in wind speed. And this can have significant impacts when you're trying to integrate renewable energy into a grid. So in particular, this period where I've highlighted with the arrow on the lower left, that is a period where the winds have decreased markedly. This is the black curve is observations taken from the ARM site in north central Oklahoma. That strong down ramp event, if the wind energy community did not know about it, they might expect the wind speeds to stay high and therefore for the production of electricity from those wind turbines to remain high also. If that wind ramp occurs, that down ramp in particular, then suddenly the energy they expected from the turbine would not exist, and that would leave the energy producer into a bind, perhaps having to buy electricity from a competitor or to emergency start some fossil fuel generation. As you can see from the version 3 of the HRRR, various forecasts that were initialized at 0, 6, and 12 UTC in brown, red, and green, those forecasts did not identify that down ramp event. However, improvements we made in version 4 of the HRRR, which became operational in December of last year, where we've improved the turbulent mixing and some of the subgrid scale drag allowed these wind ramps to be captured much more accurately, as we can see in this picture on the right, where you can see that the 6 and the 12 UTC forecasts both identified that down ramp with almost exactly the same characteristics. This gave confidence to the users of these forecasts, and they were able to plan ahead. We've also made significant improvements in subgrid scale clouds. All weather and climate models that I'm aware of struggle to represent subgrid scale clouds, clouds that are at sizes smaller than the resolution of the model. The HRRR used to have a very significant bias in the downwelling solar flux. We've made improvements to both the stratiform component and the convective component of the subgrid scale clouds. Joe Olson spoke about this earlier. And you can see in the plot in the lower left, we have this comparison with time of the downwelling shortwave bias over CONUS in the middle of the day. And the operational model at the time in blue was version 3. Our experimental model that we were running in a quasi-like operational way here at GSL was showing the same type of bias until we changed how the subgrid scale clouds were represented. And then you can see the bias dropped dramatically at that change point. Looking at the statistics over an entire year in the lower right, you can see that the bias now as a function of time of day on the x-axis is down by nearly 60%, so a marked improvement. However, statistics aren't the only way to look at it. We have to look at it spatially also. And so in the upper right, you see observations from the GOES-R satellite. And in the lower left and lower right, you can see forecasts from HRRR version 4 and HRRR version 3. These are 34-hour forecasts, so day-ahead forecasts. In the red circle, you can see the observations are clearly showing a stratocumulus deck off the coast of California. Version 3 in the lower right hardly shows any clouds there at all, where version 4 shows a much more substantial stratocumulus deck. Over Washington state in the orange circle, again, the observations are showing a low-level cloud over much of the state. Version 4 shows that there are some clouds over Washington. However, version 3 shows a clear sky scene. And then in the postfrontal clouds over Iowa in the blue circle, again, there's significant clouds in the GOES-R observations, much better represented with version 4 versus version 3. So these improvements are both qualitative and quantitative, which gives us a lot more confidence that we're doing the right things for the right reason. So our second program I want to talk about a bit is the boundary layer program that we started within OAR. So every OAR research laboratory has some interest in the boundary layer and how the boundary layer interacts with the surface below. So the figure on the right is showing the boundary layer interacting with the land surface and how changes in the sensible and latent fluxes, the way the land use, how much entrainment you have can all affect how the boundary layer evolves into precipitation, which then has feedbacks on the land itself. There are significant errors in the global forecast system, the global model that's run as part of the UFS, and the forecasts are due to errors in the boundary layer physics. So the figure on the lower right shows a plot by forecast lead time as a function of height of temperature. And so the progressive deepening of the blues, both in color and in height, is showing a progressive cold bias that builds up with forecast lead time. These errors are all rooted in the boundary layer physics. However, the research tools that OAR has, the instruments and the various modeling systems that we have, are distributed across the OAR lab system. So the boundary layer program here was an effort to bring the different labs together to all pull on the same rope in the same direction, to work together to try to improve our understanding of boundary layer physics and processes. Due to the size of the program, we had to work with other agencies to sort of maximize our efforts. So in 2018, 19, and 20, we joined an NSF-funded effort to look at clouds over the forests in northern Wisconsin. And starting in 2020, for the next couple of years, we're going to join a DOE-funded effort as part of the ARM program to look at clouds and boundary layer physics in the Crested Butte area of Colorado. The last program I'll speak about is a fire weather program. So there's been a strong desire to better understand and predict wildfire weather interactions. There's a very strong interaction between fire and weather. We can see that the number of acres burned per year has been increasing over the last several decades. There's a lot of variability year to year, but the number of acres that is burned continues to go up. The impact is even more because the wildland fire interface is starting to increase with time, and more people are living right in that wildfire urban interface area. So GSL is leading a NOAA-wide effort to support a congressional request for a fire weather program. And we're working to integrate efforts across both OAR, NESDIS, and the Weather Service One of the components of this will be to develop a fire weather testbed to help facilitate research to operations. So over the past 6 months, we've developed briefings for congressional staff and other agencies, developed a spend plan and a program change summary, which is basically a document specifying what type of research we want to do in the next 5 to 10 years. And this research includes both looking at fire weather coupled modeling, emissions from the fire and how that impacts air quality downstream, how to improve subseasonal to seasonal prediction, especially of droughts and conditions that are conducive to hazardous wildfire, and developing products and tools that we can implement into operations. So as a summary of our community activities that both Leisha and I talked about, we have a strong performance characteristics of leading multi-lab projects, including centers like the Development Testbed Center, offering tutorials and community workshops, doing testing and evaluations of modeling systems, both for the community and at GSL, and participating in a range of testbed activities. Our quality is measured through the multi-lab papers that have been published, improving models and transitioning these models into weather service operations, the release of the community models for medium and short-range weather UFS applications, and improving ensemble design and uncertainty estimates from those ensemble systems. And then the multi-lab cross-line office and cross-agency office is really one measure of our relevance in improving NOAA's research to operations, our engagement with the community, and responding to national needs. So over this last session then, the overall summary is that you've heard from our modeling efforts and how we're working to improve both regional and global modeling systems, our improvements in data assimilation techniques, working to improve predictions across a range of scales, and our community engagement. All this helps feeds into GSL's grand scientific challenge, which is to provide actionable environmental information through the delivery of global storm scale predictions and innovative decision support capabilities to serve society. Thank you.